A learner opens Java and sees three names everywhere: JVM, JRE, and JDK again. The real question is simple: can this install, run, compile, or provide developer tools? One ready-made JR only needs running. Source code needs building first before execution. So we separate these names by job, not by memorized definitions from books. The mental map is nested. JDK contains JRE, and JRE contains JVM at center. Think of the JVM as the engine in the middle. Its main job is running bytecode. Now the runtime box appears around it, because running needs more than the engine alone. Finally, the developer toolbox wraps both layers, because developers need tools plus runtime support. So the engine runs, the box supports running, and the toolbox builds and runs. Keep this picture in mind. Next we connect it to real Java files and tools. We start with the source file, the Java code a developer actually writes. Next comes JavaC, the compiler tool that belongs to the developer side. The compiler produces bytecode, usually stored in .class files the JVM understands. Only after bytecode exists does the JVM step in and execute it. That execution becomes the running application the user actually experiences on the machine. Notice the boundary. JavaC is build time, the JVM belongs to runtime. The JVM does not take the Java source file directly. That shortcut is the trap. The bridge is bytecode. Source becomes .class, and then the JVM can run it. Now we zoom into the JVM, the engine that accepts compiled bytecode. First, it loads the classes needed by the program at runtime. Then it verifies the bytecode, checking that it is valid and safe enough. It also manages memory, including objects, stack work, and automatic cleanup. Finally, it executes bytecode and turns instructions into work the machine performs. Some bytecode is interpreted. Hot parts may be optimized by the JIT compiler. The JVM implementation is machine-specific, so it can run work on your OS and CPU. The key is simple. The JVM understands bytecode, not Java source code directly. Now 4 language cards appear, because Java is not the only JVM source language. Each language can compile down to a common target, valid JVM bytecode. At runtime, the JVM mainly asks whether the bytecode is valid, not who wrote it. Kotlin or Scala source is not magically interpreted by the JVM. It is compiled first. That is why the bytecode idea matters. It explains the larger JVM ecosystem. We already know the JVM is the engine, but applications need support around it. Now the JRE appears around the JVM. This is the runtime environment. It includes standard libraries, starting with basics from java.lang that programs rely on. It also brings common support, such as java.util collections and java.io input-output classes. When a built jar enters this runtime box, the JVM and libraries can support execution. But this box does not include JavaC, so it cannot compile Java source files. So the JRE means JVM plus the libraries and files needed to run applications. Now keep that JRE box in the center, because the JDK contains it. The JDK appears as the larger developer package wrapped around the runtime. The most important tool for this lesson is JavaC, the compiler for .java files. The JDK also includes tools for packaging with jar and documenting with JavaDoc. It also supports debugging and quick experimentation, which developers use while building. And since modern Java, JLink can help create a smaller custom runtime image. This is why developers install the JDK. It can turn source into bytecode. Because it contains the JRE too, the JDK can build Java code and run it. Now split the screen into 2 jobs: building from source and running built output. On the build path, .java source goes into JavaC, so this needs the JDK. The result is bytecode, the compiled form that can move toward runtime execution. On the run path, an already built JR needs runtime pieces, not the compiler. So if someone asks whether the JRE compiles Java source, the answer is no. The practical difference is simple. The JDK builds, runtime pieces run compiled output. Now collapse the lesson into one map, starting with the JVM at center. Around it comes the JRE, adding libraries and runtime support for applications. Around both is the JDK, adding developer tools on top of the runtime. That gives us the formula. JDK contains JRE, and JRE contains JVM. They are not 3 separate alternatives sitting side by side. They are nested layers. So remember the role with the layer. JVM runs, JRE supports, JDK builds. Now apply the map to real machines. One builds, and another may only run. the developer machine needs the JDK because it works with source code and tools. After compilation and packaging, the result is a built artifact, often a JAR. That artifact moves to the runtime environment, where the job is execution. This environment only needs enough pieces to run the already built application correctly. That distinction prepares us for the modern Java wrinkle about separate JRE installs. Here is the wrinkle. Older Java advice often said, install the JRE separately. Since JDK 11, that standalone Oracle JRE installer path is mostly outdated. In practice, many developers and environments now just use a full JDK. For runtime-only needs, teams can also build a smaller custom runtime image. JLink is the tool to remember here. The classic mental formula still remains useful. First interview trap. Can the JVM run a Java source file directly? No. The JVM runs bytecode. Source must be compiled before normal execution. Second trap. Do we still usually install a separate JRE today? Usually no. Modern Java commonly uses a JDK or a custom runtime image. Keep the final hook. JVM runs, JRE supports running, and JDK builds and runs.